All right, so as usual, please type your name into the chat so that I have your record for attendance. I'll write that into the chat also, so please type your name. Okay, great. So everybody can do that, as you're here. So good. Okay, welcome everybody. Hope you had a good week. Good finishing up the end of January. So we're going to finish today our unit on circles, although of course we're not going to learn everything there is to know about circles. There's some more stuff, but I think we'll finish the basics today. And then next week we're gonna finish up kind of the geometry unit, just looking for. I'll give a kind of an overview of what are the other types of geometry. What are the other aspects of geometry that you might want to know. And then we're gonna have a break, and we're gonna decide what to do with the next unit. I would say that's not decided yet. Okay, but today we're going to finish up what we were doing with circles. So there were just a couple of homework questions, and it seems like they weren't too bad. Several people got correct answers and sent them to the list. So let's just go through them. It probably won't take too long. So the first homework exercise is, what is the circumference of a circle whose area is 8 pi? So several people got this right. So does somebody want to go through how to solve this?
Yes.
Mm-hmm. Yes. Armstrong?
Okay, the solution, right? 8 is equal to pi r squared.
Or 8 pi is equal to pi r squared, right? Yeah.
Yeah.
Mm-hmm.
All right. It divides both sides by pi.
Mm-hmm. Right. Okay. So 8
Okay,
is
you
equal to
put that on the square root.
right? So
Yeah.
r is square root of 8. Great.
Yeah. You find the factor of 8, which one will be perfect square?
Mm-hmm.
So that, I think that is 4 times 2
Right.
will be 4, 2 root 2.
Okay, exactly. Very good. So we have 2 times square root of 2. And so if r is equal to 2 times square root of 2, then the question asks for the circumference. And so what's that going to equal?
C equal, the circumference is equal to 2 r pi.
Yep. Exactly.
Then circumference is equal to 2 times 2 root 2.
Great.
Times pi.
Perfect. Okay, so that is 4 root 2 times pi, and that's the correct answer. All right, so that's completely perfect. Any questions on this solution or on the problem?
Yeah, sir.
Yes, Prince. Yep.
Prince.
Yep.
Yeah. For instance, if I want to find a perfect value of the circumference, can I simplify to go to the perfect value? Meaning, I find the root of 2, which will give me the number in decimal, then I multiply by the value of pi 3.14. So if I get my answer that way, will it be also okay?
Yeah, that's fine. I mean, of course, it's going to be an approximation in that way, but if you wanted to do some decimal approximation, you could definitely do that. So 4 square root of 2 times pi is that's 17.77, it looks like. Yeah, I mean that's fine. You just have to know that this is an approximation. The exact answer is 4 square root of 2 times pi, but the approximation is that's about 17.77 if you want to use a calculator for that.
Okay.
Yeah.
Thank you.
You're welcome. Other questions?
Yes.
Yes. Princeton?
Question.
Yeah.
Yes, we really know that the value for pi is 22/7 or 3.14. Then, if so, what we can replace the pi with the value that is given, that is constant, instead of we
Yeah.
leaving the pi?
Yeah, so I wouldn't say that the value of pi is 22/7, right? So, I mean, what we know that pi is approximately equal to 22/7, right? I mean, pi is equal to 3.14159 and like password and then some extra digits, whereas 22/7 is equal to 3.14285 dot dot dot. So like they're pretty close to each other, but they're not exactly the same. So and in particular, 3.14 is a better approximation to pi than 22/7 is. So I would really recommend against using 22/7 as an approximation of pi, right? Either I would say write the exact answer in terms of pi or use decimals, use something like 3.14, because 22/7 is just like not that good an approximation. And it's also not that nice looking. Like once you're going to have fractions like this, if you want to understand your answer more easily, it's better to just use decimals. Yeah. So, I mean, the value of pi doesn't need to be given, right? I mean, the value of pi is what it is, right? But I would say if you want an exact answer, it's best to just leave it in terms of pi. If the question said, what is the answer accurate to 2 decimal places, then you want to convert to decimals and write something like 17.77. Right? I mean, if you're actually trying to measure this circumference, then having the decimals is going to be useful. It's very, very rare that having this approximation 22/7 is going to be helpful. For the Greeks, maybe that was helpful because they didn't have calculators, so this was a way that they could compute. But now with calculators, there's just kind of no reason to use 22/7, right? You may as well use pi, or if you want to restrict to a few decimal places, you can use 3.14. But I wouldn't use 22/7.
Yeah, thank you.
You're welcome. Good. Other questions?
Hello.
Hello, yeah, Marcus?
Hello.
Yeah, Marcus? Oh, no, sorry. Is that
Yes,
William or Marcus? Yeah.
Yeah, Marcus. I'm not seeing the solution on my screen. I don't know why.
That's got to be on your end because I think it's showing up for people's screens. It should be what you see if you just have the Zoom app open. Should be what you see on Zoom. I think it's showing up okay. Yeah, it may just be your connection. Or network.
Okay.
Yeah. Sorry about that. All right. Other questions?
Here, we are
Okay, let me just mute everyone. Okay. Okay, so let's go on to the next question. Okay, so in the figure below, given that angle ABC is 60 degrees and angle BCD is 70 degrees, find angle CBD. So I need to redraw the picture. So let me just do that. 1 second. Let me do that picture. Okay, where are we? 119. Oh, do I not have the handout? Handout. I think I never put this back on my computer, so give me 1 second. I need to just find the handout here. So what did the diagram look like? Here. Okay, so this is 60 and a 70, A, B, C, D, 60 and 70. Okay, so let's try that. Okay, so let me just recopy the picture here. So we have a circle. We have a tangent line drawn to the circle. And we have a triangle like this. That's triangle. And so we have 70 degrees here. This is C, this is B, this is A. This angle here is 60 degrees. And this is point D over here. And we're trying to find angle CBD. So that's this angle right here that we're trying to find. Okay. So, and maybe let me just, before we do this problem, let's just recall that when we have we have certain formulas for how to get angles, right? An inscribed angle is an angle formed by two chords of a circle meeting at a point, and its measure is half the measure of the arc that it cuts out. And this tells us that any two inscribed angles cutting out the same arc are equal. And then we also have this result that the angle formed by a tangent line and a chord of that circle is half the arc measure cut out by the chord on the correct side of the tangent line. Okay, so these are these two results that we did last week, and you're going to need to use at least one of them in order to solve this problem. So going back to here, I give you these two angles, and the question is, how can you find angle CBD over here? Okay, so does anybody want to give a solution? And I think one of the things that we mentioned last time is it might be useful to label another point here, call it E.
Yeah, Clinton.
Yeah, Clinton, hi.
Yeah, I think to find angle CBD, we need to know angle DBE.
Right.
And angle DBE has a relationship here. It's equal to 70 degrees because, so angle DBE is 70 degrees because angle DCB and angle DBE cut out the same arc.
Right. Right. So does everybody see this here? If we take this angle DBE, this is a tangent and a chord, and so the angle is half the measure of this arc. And if I take angle DCB, or BCD, it's the same thing, this also cuts out the same arc, and it's also half the measure of that arc. So since both of these angles are half the measure of this arc BD, that means they have to be equal to each other, okay? So I'll say since angle DCB is 70 degrees, we have that angle DBE, as Clinton said, is also 70 degrees. So let me just label that in a different color here. So over here, we have 70 degrees. Okay, great. So continue.
Okay, so once we find angle DBC, we can use the straight line angle properties because we have three angles here on a straight line. Angle ABC and our unknown angle CBD and angle DBE. These three angles falls on a straight line, so we add the three of them and equal to 180.
Right, exactly. So let's call, so what we have is that, so since these three angles are on a straight line, one of them is 60 degrees, one of them is 70 degrees, and the other one is the angle we want to find, which is angle CBD. So we have, so 60 degrees plus angle CBD plus 70 degrees equals 180 degrees, right? And so then we solve for angle CBD, and what do we get? 50. Okay, so I see in the comments 50 degrees from Princeton. Yeah, so that's exactly right. So 50 degrees. All right, so that's great. And that's completely correct, 50 degrees. So there's actually another solution, which is what I had in mind when I first thought of this problem. So I'll tell you what my other solution is. So this solution is completely correct, and it's a great solution. So the other solution I had in mind is that, well, we know that if this red angle here is 60 degrees, that the corresponding arc that it cuts out has to be twice as much, right? So that means that this arc here, arc BC, is going to be 120 degrees, right? That's like arc BC, so I'll draw it in purple. Now, we also know that if this angle here is 70 degrees, that means that this arc that it cuts out has to be 140 degrees, right? Because it has to be twice as much as the inscribed angle, right? So this would be 140 degrees. And now, well, the full circle is 360 degrees. So I have 120 here and then 140. So that's 260 degrees. And so there's one more arc left. And so this arc over here has to be 100 degrees in order to make everything add up to 360. So this is 100 degrees. And then if I know that this arc is 100 degrees, that means that this angle right here has to be half that. So the angle has to be 50. So I would say, so angle CBD is equal to 100 degrees divided by 2, which is equal to 50 degrees. Okay, so this is just a different solution. So you can do the whole problem based on looking at arcs, if that's what you want to do, or you can do it based on showing that this angle is 70 degrees and having all the angles add up to a straight line. Both of them give you the same answer, 50 degrees, which is the correct answer.
Yeah, Andrew.
Yeah, Clinton?
Yeah, just make a comment as well.
Yep.
So angle D here, another method we could use is that angle D here is 60 degrees because angle BDC and angle ABC cause the same cut out the same arc.
Exactly, right. So angle, let me just show it for everybody. So angle D here cuts out arc BC, and this tangent angle here also cuts out arc BC. So from that, you can conclude that angle D has to have the same measurement as angle ABC, right? So that means this angle has to be 60 degrees. And so continue.
Yeah, so now we have a triangle, and the angle which we want to find is one of the missing angles of the triangle, or actually is the only missing angle of the triangle. So we add these three and equal to 180.
Exactly, right. So you know you've got a triangle. If one is 70 degrees, another angle is 60 degrees, they have to add up to 180. The only way for that is for this to be 50 degrees. So yeah, so it's really three different solutions. And in geometry, there's often lots of different ways to solve the problem. And hopefully they should all give you the same answer. So yeah, so this is another really good solution. Okay, so there's a question. Sorry, there's a question in the comments. So what if angle CBD was given and angle BCD was not given? So if I didn't give you this, but I gave you this one instead, that would be not enough information to solve the problem. Because what we see here is that if I gave you this 60 degrees here, which is part of the givens, then this angle CDB is just also 60 degrees. It has to be 60 degrees. It can't be anything else. And if all I told you is that both of these angles are 60 degrees, then you wouldn't have enough information to solve the problem. So you really need this angle to be given. If I just gave you that BDC is 60 degrees, then that wouldn't be enough information to solve the problem. Okay. Other questions or comments?
Yes, sir.
Yes, Prince.
Yeah, I just want we just solved this problem. Clinton to look at it here, Kine. I really want to look at it here. Where you got this 60, what is the relationship between the 60, which is angle ABC? What's the relationship between them before you get angle B, C, D, this 60? I want you to
So what's the relationship between the two different 60-degree angles?
Very good, very good.
Right. So this angle is an inscribed angle, and the arc that it cuts out is BC, right? That's its arc, this angle. This angle is formed by a chord and a tangent, and the arc that it cuts out is also BC. It's the same arc, right? This angle and this angle cut out the same arc, right? And for both inscribed angles and chord tangent angles, the formula for the angle is 1/2 of the arc measure, right? So since these angles both cut out the same arc, they both have measure 1/2 that arc. And that's why they're both 60 degrees. Is that good?
Yeah.
Okay, great. And it's the same thing with these 70 degrees. We have this angle is 70 degrees EBD, and it cuts out this 140-degree arc. And this angle is 70 degrees BCD, and it cuts out the same arc, BD, which is 140 degrees. Yeah. All right. Any other questions? Yes. Question?
Emmanuel,
Yes.
are you getting?
Yeah, I'm getting you not so well, but a little bit.
Okay, this is
Oh,
Emmanuel.
Emmanuel, hi.
Bichir.
Hi. Yes. Better.
How are you?
Good. How are you?
I'm following, but I've been having some problems on phone. I think
Okay.
it's improved now a little bit. Yeah, I was looking at angle B,
Mm-hmm.
and I'm sorry I came a little late. Can you please clarify how you derive angle B and angle D?
Angle D, yeah. So angle D, this is what I said, right? So this angle ABC is 60 degrees. This is given, the 60 degrees here. And then,
Okay.
right? And so angle D over here, if you look at its arc is the same arc as the arc for this angle, for ABC. So since they cut out the same arc, they have to have the same measure. So if this is 60 degrees, this has to be 60 degrees also.
Okay. Thank you.
You're welcome. Okay. All right. So let's move on just so we have enough time to do our new thing. So okay, so we recalled this. This is fine. Okay, so I want to give one proof because this inscribed angle formula is kind of a very nice formula, and I think it looks like magic, and we should give a proof. And the proof is not that hard once you realize what's the correct thing to draw. So here I'm going to draw a circle with an inscribed angle. I'm going to call it ACB. And I'm going to call this angle here theta. Okay? And so what I'm also going to draw is the center of the circle here, which I'm going to call O. And I'm going to draw the central angle that cuts out the same arc. Okay, and I'm going to call this phi. Okay? And so what do we want to know? We want to show, well, we know that phi, the measure of phi is just the arc measure of AB, right? Because this is a central angle. That's not really a result. That's more or less telling you, that's just the definition of arc measure, that whatever this arc measure is the central angle over here. So phi is the measure of arc AB. What we want to prove is that theta measures half the measure of arc AB. So what we really want to show is that theta is equal to 1/2 of phi. Or multiplying by 2, what we want to show is that 2 theta is equal to phi. Okay, this is what it means to prove the arc formula here, is you want to show that if you have an inscribed angle with a given arc, that its measure is half the central angle with the same arc. So if this arc was 60 degrees, then phi would be 60 degrees. And what we want to show is that theta is half of that, that theta is 30 degrees, right? So what we want to show is that 2 theta equals phi. Okay. And what happens here is that with a lot of geometry proofs, you kind of just need an idea to draw the correct line or lines. And once you draw the lines and label everything correctly, then the proof can actually be very short. So what I'm going to do is I'm going to draw 2 extra lines here. Okay, I'm going to draw this line over here, and I'm going to draw this line over here. This line over here. So we have a kind of kite-looking figure. Okay. And I'm just going to give all of these angles names. So I'm going to call this V, X, Y, Z, and W. Okay, this is just going to be the names of all of these angles. Okay, and this angle I'm not going to use, so I don't need to name it. Okay, so now I'm just going to write out some equations. Okay, so the first equation is that, well, I have triangle ABC. We know that all of the angles add up to 180 degrees, right? So if I take theta plus X plus Y plus Z, that has to be 180 degrees. So theta plus X plus Y plus Z equals 180 degrees. Okay. Similarly, I have this triangle ABO, That's also a triangle. So everything adds up to 180 degrees. So that tells me that phi plus W plus Y plus Z equals 180 degrees. So phi plus W plus Y plus Z equals 180 degrees, right? Maybe I'll say that the first one, this is from triangle ABC, and this one here is from triangle AOB. Right? I'm just adding up all of the angles in the triangle and saying that it's 180 degrees. Okay? So now I have two more identities. So the thing to notice is that if I draw a triangle with center at the center of the circle, with a point at the center of the circle, and I draw two radii, all of these radii are isosceles, all these radii are equal, right? Because they're all the radius of the circle. So I'm just going to observe over here that the length of OA is equal to the length of OB, and that's equal to the length of OC as well. They're all the same. So that means that we have a lot of isosceles triangles here, right? We have AOB is isosceles, and AOC is isosceles, and BOC is also isosceles. So if we look at this isosceles triangle over here, BOC, right? This is isosceles, and one thing that we know about isosceles triangle is that the angles are equal. The angles opposite the equal sides are equal. So we get here that V is equal to W, and this is because triangle BOC is isosceles. Okay, so these two angles, angle V has to be equal to angle W. And now also, because this triangle here is isosceles AOC, this tells me that angle X, this angle has to be equal to this angle. So X has to be equal to theta plus V. So I'm going to write X equals theta plus V. This is because triangle AOC is isosceles. Okay. And so now I claim with these four equations, I have everything that I need to do the proof, right? So let me give these equations numbers. We'll call this equation 1, equation 2, equation 3, and equation 4. Okay, so equation 1, equation 2, equation 3, and equation 4. Okay, well, what I'm going to do is I'm going to substitute equation 3 into equation 2. So if V is equal to W, I can replace this W with a V, right? So let me just do the proof over here. So subbing 3 into 2, what do I get? I get that phi plus V plus Y plus Z equals 180 degrees. Okay, I'm just replacing the W with a V. I can do that, right? So instead of phi plus W plus Y plus Z, I get phi plus V plus Y plus Z is 180 degrees. Now, likewise, with equation 1 over here, I know that X is equal to theta plus V. So I'm going to make that substitution. I'm going to substitute 4 into 1. So subbing 4 into 1, I get that theta plus V plus Y plus Z equals 180 degrees. Or that says 2 theta plus V plus Y plus Z equals 180 degrees. Well, what do I have? Well, phi plus V plus Y plus Z is 180, and 2 theta plus V plus Y plus Z is 180. So both 2 theta and phi are angles that when you add them to V plus Y plus Z, you get 180. And so what this tells us is that 2 theta has to equal phi, right? Or we could subtract, the bottom of equation from the top equation, and we get that phi minus 2 theta equals 0. So we could say this, subtract the bottom from the top, and we get phi minus 2 theta equals 0 degrees, or phi equals 2 theta. And this is exactly what we wanted to prove. Right? We wanted to show that 2 theta was equal to pi, sorry, 2 theta was equal to phi was equal to 2 theta. And so we drew all these angles, and then we get all these equations, one coming from this triangle ABC, sum of these angles is 180, one coming from this triangle AOB, sum of all of these angles is 180. And then from the isosceles triangles, we get that V equals W, because they're in an isosceles triangle. And then we also get that X is equal to theta plus V, because they're in an isosceles triangle. And once we have that, then we can do some algebraic substitutions, and we end up deriving that 2 theta is equal to phi. Okay, so this proof is a little bit complicated, but it's telling us that the central angle is always twice the inscribed angle when they have the same arcs. Okay. So that's how the proof of this works. That's why we have this half angle formula, that the measure of an inscribed angle is half of the arc that it cuts out. Okay, so any questions or comments on this?
It's understood to
Okay,
me,
good.
sir.
Good. Okay, so I figured I'd just give you that proof. Another thing that I want to mention, which is maybe somewhat interesting, is we already saw in the problem that a chord tangent angle had the same formula as an inscribed angle, right? Both of these were half of the arc that it cuts out. So I want to give an argument why that's true. So let me just see. Techno K, I5K. No, K, I5K, please. Okay. So, all right. So let me draw a picture here. So I'm going to take another angle here. So this is going to be A, this is going to be C, and this is going to be B. So I look at this angle. Okay. So I have this angle right here. And I want to know what happens as I move the point A closer to the point C. So I'm going to go make this as short as possible, right? So we know we know that angle ACB is equal to 1/2 of the measure of arc AB, right? Which I'll write like that, measure of arc AB. Right, this is our inscribed angle formula. We know that this angle is half the measure of this arc. And we know that this formula holds no matter where A is, right? So if I move A closer and closer to C, the arc is going to get bigger. That's going to make the angle bigger. And so the question is, what happens to the angle as A gets closer to C? And what actually happens, this is not really a proof, it's just kind of a little justification, is that as A moves closer to C, the line through A and C actually becomes the tangent line through C. So if you've had any calculus, this is kind of saying that the tangent line is the limit of secant lines, which is what you do when you define the derivative. Okay, and if you haven't had calculus, that's fine too. Let me just show what's happening here is right. The angle gets bigger, as James said. And really, as the A moves towards C, we're going to get the line through C and A, and all of these lines through C in a close by point. And as A gets very close to C, then the line in the end actually becomes this tangent line. Okay, maybe I'll draw the whole line instead of just the line segment. So maybe you can see as I move A closer to C, what happens to this line through C and A is that it becomes the tangent line, right? So this would be, you know, C, you know, equals A over here, right? So if I'm asking, like, what's the line from like a point and itself on a circle, what's really happening is that if you imagine rotating this line through A as A gets closer to C, the line is going to end up in the limit just being equal to the tangent line. Was there a question?
Yeah, yeah, something I wanted to
Yes.
get French.
Mm-hmm.
Yeah, you said if we can, is that by extending the line or to just take a line from A point to just be breaking it down? It's just about extending or to just take.
Exactly, right. Yeah. So it's usually we draw only this line segment from A to C, but I can draw the whole line. That doesn't change the angle at all, right? So this demonstration is a little clearer if I draw the whole line. So because that way, when A goes to C, I still have a whole line. I'm not getting something that's just disappearing, right? So the whole line, if I had my A over here, would really look close to the tangent line. And the more I move A towards C, this whole line is just rotating a little bit. It's rotating until I get to the tangent line there. So it's easier to draw the whole line because if I just draw the line segment, then that'll just disappear when A gets to C. But if I draw the whole line, then it'll still be a line. It's just going to be tangent instead of a chord. Okay. So, okay. So we have this tangent line, and let me still draw CB. That's the same as before. And so what we know is that at every step, the angle is half the arc, right? And everything here is continuous, right? The angle is continuously growing. The arc is continuously growing. So at every step before A gets to C, the angle is half the arc. And so since that relationship is constant and everything is continuous, what happens, and of course, to make this rigorous, you have to actually use some limits, but what should be kind of intuitive is that that relationship, that the angle is half the arc, that holds for every A, no matter how close it gets to C. So in the limit, it should also hold when A is equal to C. Okay, this relationship that the angle is half the arc. So what I'll say is that this remains true when this remains true when A gets all the way to C. Okay, so every step over here, the angle is half the arc. I keep moving A towards C. At every step, the angle that I make is going to be half the arc AB. And so when I finally get to C, this angle should still be half the arc. Okay, this is not a proof in the sense of Euclid. Okay, there are other ways of actually proving this in the sense of Euclid. But what I think it is it's a good justification that provides some intuition for why the chord tangent formula is the same as the inscribed angle formula. And what you should think of it is that the chord tangent diagram is just the limit of the inscribed angle diagram as the point A goes toward the point C. So as it gets closer and closer to C, what happens is that this line goes toward the tangent line and the arc goes toward arc AB, and the relationship between the two is still going to hold. Okay, so this is maybe just an idea of why your chord tangent formula is the same as the inscribed angle formula. Okay, I'm not going to say anything more about this. Yeah, Clinton?
Yeah, thank you. That's a great justification because I've been wondering on this. But what if we consider the case where A moves further away from C? What happens as we move the point A further away from C?
So if you want to move it toward B?
Yeah, sure.
Yeah, so it's going to be the same thing, right? But in that case, if A moves toward B, then you're going to get the tangent line at B instead. And so if A moves over toward B, then you're going to have well, okay, I mean, if A moves toward B, that's just 0, and so the angle just becomes 0, right? If you're trying to measure angle ACB. If you
Yeah,
want
yeah,
A to
sure.
move toward B and you're going to measure angle ABC, then you're going to have the same picture but in mirror image. So you're going to have a tangent line at B, and it's going to be equal to half the length of this arc because you're really going to be measuring the arc AC in that case.
So if A moves towards B, in which case A equals to B,
Mm-hmm.
would this not just be the core CB?
Yeah, the arc would be CB. It would be 1/2 if I did the tangent line at B. Well, the chord C, it would just be the chord CB, right? So if A just moves toward B, then you have CB and CA would be the same thing. So the angle is just 0, and that makes sense because the arc from A to B is also 0. Yeah.
Okay. Yeah, sure.
Yeah, that works. Yeah. So everything's just 0 in that case. Okay. Okay. Okay, so this is a demonstration why the tangent property works, although it really, to make this rigorous, you need to use calculus and you need to use limits, and I'm not going to do that now. But at least we can understand why the formula makes sense. Okay, good. Other questions or comments? Okay, so let me say one other thing. So a consequence of the inscribed angle formula for something called a cyclic quadrilateral, right? So one thing that we talked about when we did regular polygons is we said that every regular polygon, no matter how many sides it has, always has a circumscribed circle, right? So if I draw, I mean, I'll just draw a little thing. So if I have like a little, a regular pentagon, then there's going to be a circle around it. That's not so good because it's not really a regular pentagon. Let me try that again. Every regular pentagon, it's hard to draw a regular pentagon. How about like this? This looks better. That looks a little better. So any regular thing is going to have a circumscribed circle. Let me just not try to draw this because it's not going to be good at that size. Okay, but we saw this when we were defining the in radius and the circumradius for a regular polygon. So in fact, every triangle has a circumscribed circle, regardless of what the triangle looks like. It doesn't have to be a regular or equilateral triangle. It can be any triangle at all, and it's always going to have a circumscribed circle. But in fact, it's not true that every quadrilateral has a circumscribed circle. And what's a reason why not? Well, let's say that I have a quadrilateral with a circumscribed circle. So a circumscribed circle just means a circle that goes through every vertex, right? So if I have something like this, let me label these points A, B, C, D, E. So no, sorry, A, B, C, D. So what we have here, if I have a quadrilateral like this, well, angle D in this case, well, that's an inscribed angle. So it's equal to 1/2 arc ABC, right? So angle D equals 1/2 arc ABC, right? That's exactly what the inscribed angle means. And angle B, on the other hand, well, that's an inscribed angle here. And so if I look at this arc, which is arc ADC, we have that angle B equals 1/2 arc ADC, right? So what if we add them together, angle D plus angle B? This is equal to 1/2 arc ABC plus arc ADC. But what do we have here? ADC is this part of the circle. Sorry, ABC is this part of the circle, and ADC is the other part of the circle. So together they make the full circle. So this is equal to 1/2 times 360 degrees, which is equal to 180 degrees. So what we see, so I'll just write that down. So angle B plus angle D is equal to 180 degrees. And you can make a similar argument. Similarly, angle A plus angle C is also equal to 180 degrees. So this tells us that if you have a quadrilateral with a circumscribed circle, this is sometimes called a cyclic quadrilateral, then if you look at the opposite angles, they have to add up to 180 degrees, right? So a quadrilateral with a circumscribed circle has opposite angles adding to 180 degrees, okay? And this means that if you have a quadrilateral that doesn't have this property, then it can't be inscribed in a circle. It can't have a circumscribed circle. It can't have a circle that passes through all of the points, okay? So just by virtue of the inscribed angle formula, the only way you can put a quadrilateral in a circle is if the opposite angles add to 180 degrees. Okay. And these types of quadrilaterals are sometimes called cyclic quadrilaterals because they live inside a circle or a cycle. So they call them cyclic quadrilaterals. So just as an example, which I'll write on another page. So an example, let me just add another page. So if I have a rhombus like this, if I have a rhombus that looks like this, with these angles are both 40 degrees and 40 degrees, and these angles are 140 degrees and 140 degrees, that's 360, then this quadrilateral is not cyclic. It's not cyclic, and that's because if I look at the opposite angles, they don't add up to 180 degrees. This is because, 140 plus 140 is not equal to 180. And likewise, also these two opposite ones, 40 plus 40. So 40 degrees plus 40 degrees is not equal to 180 degrees. Okay, so it's a check. The only way you can, so there's going to be no circle that passes through all four of these points. Okay. And the only way it can actually lie inside is if the pairs of opposite angles add up to 180 degrees.
Yeah, Andrew?
So, yeah.
Yes.
Question? Yeah, Clinton?
Yeah. So with the exception of a quadrilateral, do we have other polygons? Do we have other polygons that are cyclic?
Well, so there are, right. Of course, I can just take any circle and just pick out some points on the circle and connect them, and I'm going to get a cyclic polygon, right? So this is a cyclic hexagon because I just drew it, right? So you can always find cyclic polygons, but once you get above triangles, if you just draw a random polygon, it will usually not be cyclic. Okay, it has to have a very special property to be cyclic. Okay, and for quadrilaterals, this is the property, and for higher sided polygons, then the property gets more complicated. There's more things that have to be satisfied, and it's less likely that if you just draw a pentagon or a hexagon, it's less likely that it will be cyclic. So they exist, but they're rare. Whereas for triangles, it's every triangle.
Yeah, so you said if we get beyond a triangle, so does that mean that we have a cyclic triangle as well?
Every triangle is cyclic. Every triangle, and I did not prove that. That requires a proof. But every triangle can be inscribed in a circle. So every triangle is cyclic.
So can we also consider the argument of opposite angle as well?
Well, opposite angles also, but you need to make it a little bit more. You need to make it a little bit more careful. So with a hexagon, for instance, it's not good enough to just have the opposite angles because the opposite angles their arcs don't form the whole circle. There's going to be some overlap here. So what you need to do is actually, I think you need to basically look at this angle plus this angle plus this angle, like the three here, they need to add up to half the total angle measurement of the hexagon, and this angle plus this angle plus this angle also need to add up to half the total measurement of the hexagon. And I think you might need even more than that. I think that might not be enough to guarantee that it's cyclic. I don't remember for higher polygons exactly what the condition is, but the conditions get more complicated the more sides you have.
Okay, so can we just quickly look at this argument for quadrilateral? Can we just look at it for triangle?
Yeah. Mm-hmm. So, you mean for triangles?
Yeah.
Look at it for triangles. Yeah. So for triangles, you don't have the exact same argument, right? Because triangles, if you try to do a triangle, you try to make this argument with a triangle, you don't really have any opposite angles, right? So for a triangle, all that you have is that if this is angle A, this is angle B, this is angle C, you have that angle A is equal to 1/2 arc BC, right? Angle B is equal to 1/2 arc AC, and angle C is equal to 1/2 arc AB. And if you add everything up, then you just get that angle A plus angle B plus angle C equals 1/2 arc BC plus AC plus AB, which is the whole circle. So that's 1/2 360 degrees, and that's 180 degrees. But this just doesn't tell us anything. All this tells us is that the sum of the angles in the triangle is 180 degrees, right? And that's true for every triangle. So it's reasonable to believe, this is not quite a proof, but it's reasonable to believe that every triangle can be put in a circle, because the only condition we get from these arcs is that the sum of the angles is 180 degrees. And we already know that the sum of the angles is 180 degrees. So this isn't really placing any restrictions on the triangle.
Okay, all right.
Okay. Yes, this is what happens if you try to do the argument for triangles.
So now in summary, when we say that the argument for quadrilateral being cyclic is that opposite angles are supplementary.
Yeah.
And that for triangles, the argument for a triangle being described in a cycle is that the sum of all the angles equal 180. Is that?
Sure. Yeah, but that's true for every triangle.
Yeah, obvious.
Yeah. So,
okay.
Yeah, so that's how it works for triangles. Okay, other questions? Theophilus, do you have your hand raised?
Yeah.
Yeah, question?
Okay. Internet.
Sorry?
Hello?
Okay.
Hello?
Yeah, hello, question?
Yes, question.
Princeton, yeah.
Yes, you did mention that only a quadrilateral that is not cyclic. Now, can we, as looking at triangle also, so you don't think triangle is also part of it? Because the triangle doesn't have an opposite angle there. But you did mention that only, let's say it's quadrilateral, it's not cyclic. So can we also consider triangle not to be cyclic?
Yeah, well, no, every triangle is cyclic. And the point is, if I have, let's say I take the triangle with 3 sides of this quadrilateral here. I don't want to draw it because I don't want to clutter the diagram, but I can find a circle that goes through these 3 points. So that's going to be a cyclic triangle, but this circle is not going to go through the 4th point. And so you can't get it to pass through all 4 points. You can only get it to pass through these 3. Yeah. Yeah, every triangle is cyclic. Yeah.
Okay. So from here, now from this end, I've understood, because drawing a circle on this quadrilateral will not go straight.
Exactly.
Yeah. So because now going straight, it becomes not to be cyclic.
Right. You can draw an ellipse that will pass through all these points, but not a circle.
Yeah, not yet.
Yeah. Okay. Theophilus, do you have a question? Okay, so it's okay. Okay, good. So let's just move on to the last thing I want to say about circles. Right, so James mentions there's 4 triangles within that cyclic quadrilateral. That's true. I can take any set of, I can leave off any point, and that'll give me a triangle. So I have this triangle, I have this triangle, I have this triangle, and I have this triangle. And for each of those triangles, there's a circle that passes through all 3 points. but it will never pass through the fourth point, because that's when you have this non-cyclic quadrilateral. So the circle will never pass through the fourth point. Okay, good. Okay, so the last thing that I want to do, fairly quickly is if we consider a circle in the plane with center at the point AB and radius r, what can we say about a point xy that lies on a circle? So let's now move back to the coordinate plane. So if I have a point here, AB, which is going to be the center of my circle, and the circle has radius r, and this is a point xy over here, then this means that the distance from AB to xy is equal to r, right? And what we have here is if I draw this right triangle, the height change here, this is y minus b, and the length change to the side here, this is x minus a. And so by the Pythagorean theorem, by Pythagoras, we have that x minus a squared plus y minus b squared is equal to r squared. Okay? And this is what we call the equation of a circle. Okay? So if I have a circle whose center is at the point AB and whose radius is r, then we can have, if we want to draw the equation for a circle in terms of two coordinates, x and y, the equation that we get is x minus a squared plus y minus b squared equals r squared. So we look for the x's and y's that satisfy this equation, and those are exactly going to be the x and y that are at a distance r from the center AB. Okay? So this is what we call the equation of a circle. If you want to graph the circle using an equation, this is what we use. Okay? And I think we have a basic example. So let me just do a basic example. So a circle with radius 3 and center at 1, 2 is just going to be given by x minus 1 squared plus y minus 2 squared equals 9. Right? So this is how we do the equation of a circle. Okay? So usually you've been talking in Euclidean geometry, we're usually not using coordinates. We're just drawing geometric figures and trying to prove things about them. But sometimes it's also helpful to have coordinates and to have graphs. And so when we're doing an equation for circles, we have this not such a complicated form, right? You need the center here, x minus a squared plus y minus b squared equals r squared. Okay. So this should be, I think, familiar to most of you. And so what I want to say is, how can we recognize an equation for a circle when it's not necessarily given to us in exactly this form? So what I want to recall is a technique for solving a quadratic equation, which is called completing the square. So let's suppose you want to solve the quadratic equation x squared plus 10x plus 21 equals 0. So you can factor this. And if you see how to factor this, you'll see it's x plus 3 times x plus 7 equals 0, and you can solve it that way. But another way that you can do it is something that's called completing the square. And the way you do that is you write x squared plus 10x plus 21 as x squared plus 10x plus 25 minus 4, right? I mean, that's totally fine, right? 21 is the same thing as 25 minus 4. So I can do that. But the advantage to writing it this way is that when you write it like x squared plus 10x plus 25, you recognize this as a square. This is the square of x plus 5. So another way to write this is x plus 5 squared minus 4. So x squared plus 10x plus 21 is x plus 5 squared minus 4. And now this is an easy equation to solve. So if you want to solve x plus 5 squared minus 4 equals 0, which is the same equation that you started with, this is easy because you just move the 4 to the other side. So you have x plus 5 squared equals 4. And so that's going to give you x plus 5 equals plus or minus 2. You just take the square root of both sides. And once you have x plus 5 equals plus or minus 2, then you just solve the two different equations. And one of them is going to give you x equals 7. And the other one's going to give you x equals minus 7. And the other one's going to give you x equals minus 3. And I'll just say, as an exercise, this is the same answer as factoring. gives. And it's the same answer as the quadratic formula also. In fact, the way that you prove the quadratic formula is by completing the square. There's not enough time to say more about that now, but maybe at some point I'll show you that, not today. Okay, so this is just a review of this completing the square, which is one of the methods that you can use to solve the quadratic equation. Okay, is this familiar to most people?
Yeah, sure.
Yes.
Good. Okay, so let me go to the last slide today. So the technique of completing a square can help us extract information from the equation of a circle. So let's say I give you an equation like this. X squared plus y squared plus 4x plus 6y equals 29. Okay? So the question is, what are its center and radius? I just want to make sure I didn't do this badly. Okay, yeah. Okay, this is fine. So what are its center and radius? Well, one thing that I can do is try to complete the square on the left-hand side. So complete the square. Well, this is x squared plus 4x. Well, what I can do is add 4 to it, which is going to make it x plus 2 squared. And then y squared plus 6y, I can add 9 to it, which is going to make that y plus 3 squared. And this is going to be 29, but I added a 4 and I added a 9, so I've got to add the 4 and I've got to add the 9 over here, right? All I did was rewrite the equation by adding a 4 and a 9 to the left side so that I could get a couple of squares, and then I have to add the 4 and the 9 to the other side. So this is going to be x plus 2 squared plus y plus 3 squared equals 29 plus 4 plus 9, which is 42. And now this is the more familiar equation for the circle, right? So for this equation for the circle, now we can just read it off. The center, well, maybe I'll do one more step. This is the same thing as x minus minus 2 squared plus y minus minus 3 squared equals 42. And what this tells us is that the center has to be the point minus 2 comma minus 3. And the radius, remember the formula for a circle, the center is a and b here, and the radius is just what we have on the right side is r squared, so the radius is the square root. So the radius in this case is just going to be equal to square root of 42. Okay? So by completing the square, you can take an equation that doesn't exactly look like the standard form for a circle, and you can convert it to an equation that is in the standard form of the circle. You have to just add the correct numbers that are going to make everything into squares. And once you do that, then you can read off what the center and the radius are. The center is going to be minus 2 minus 3, and the radius is going to be the square root of 42. Okay, so that's an example of completing the square in order to get the equation of a circle. Okay, questions?
Andrew.
Yep.
Yes, sir.
Yes, question.
So it's
Prince.
definitely what you definitely what you do is by taking half of the 4x and that the 6y. That's why I gave you 4 and 9. Is that what you did?
Right, exactly, yeah. So I didn't go through the details here, but yeah, the way I know to do 4 is I take half of the 4, that gives me 2, and then I square it to get 4. And here I take half of the 6, that gives me 3, and then I square it to get 9. And that's exactly what's going to give you something that's a square. Good,
Yes,
good. Thank you for the comment. Yeah.
Let me just add up to what you said.
Yeah.
Always when you are using the complete square, it tells you that you should take the half of b. So the half of b that will be there. So then you have s squared plus 4s. So 4s now become b. So half of that 4 now will be 2.
Exactly.
That's an easy way to do that. And whatsoever that will be half on your left hand side should be square at the right hand side.
Exactly. Yeah. Yeah. So that's exactly right. Okay.
Okay.
All right. So, okay, so we're just about out of time. So let me say, so for homework exercises, so we have one exercise, which is kind of similar to this last one. So find the center and radius of the circle that's given by this equation. X squared plus y squared plus 8x minus y equals 20. So 2 and 3 are more geometry questions. So 2 is, suppose a circle is inscribed in an equilateral triangle, and we want to know what is the ratio of the circle's area to that of the triangle. So let me just draw a picture for number 2 so that you can see it. So I have an equilateral triangle over here, and then I'm going to draw a circle inscribed in that triangle like this. Okay. This is my circle inscribed in the triangle. And one fact that you're allowed to use is that the radius of the circle here is 1/3 of the altitude of the triangle. So this right here, and then let me just draw the rest of the altitude in green. So you can use that the red, you can use that the red, why is this not working? Red is equal to 1/2 of red plus, sorry, 1/3 of red plus green. Delete this. Okay, so you can use that the center of the circle over here is going to be 1/3 of the entire altitude. So another way of saying this is that the red line is 1/2 of the green line. Because if this was 1, then the whole thing would be 3. So the green would be 2. Okay. So so you can use that, then you can calculate, I claim you can calculate the ratio of the circle's area to the area of the triangle. So part 3 is the same question, but now with a circle inscribed in a square. So the question 3 is actually easier than question 2. So here I have a square, and I have a circle inscribed in the square, and I want to know what's the ratio of the circle's area to the triangle's area. Okay? And the question, and then the extra question is this ratio smaller or larger than in the case of the triangle? So if I have a circle inscribed in a square, does it fill out a larger proportion of the area of the square or a smaller proportion of the area of the square relative to the case of a triangle? Okay? And then the question is, does this suggest a pattern to you? It's like, what would happen if we had a pentagon or a hexagon, a regular pentagon, a regular hexagon, and tried to inscribe a circle in it? Would it fill up more of the area or less of the area? So we'll discuss that a little bit next week. Okay, so let me remind me, this is an equilateral triangle. Good. Okay, so these are the homework problems for this week. Of course, I'll send out the notes on WhatsApp after the class is over. And so thank you for your attention. And next week, we're going to finish up our geometry unit with kind of an overview of, what comes next in geometry. Okay, and then just as a preview, there's going to be no class on February 9th. Okay, and then resume on February 16th. Okay. Okay, any questions? Oh, and if you have not typed into the chat anything yet, please type your name into the chat so I have a record for your attendance. And in particular, Techno 5KI 5K, we don't know who you are. So can you please type in your full name?
Hello.
Hello, Sange?
Yeah, so next week we have class for week after no class?
Yes, correct.
Dr. Obos?
Yes, hi.
Christopher.
Oh, hi, Christopher. Oh, okay. Are you the you're the Techno KI 5K?
Yeah.
Okay.
Yeah, but rename.
Okay.
Yeah.
Let me just type in your name so that we have it. Okay. Okay, thanks.
Thank you, Dr. Obos.
Okay, you're welcome. Anything else?
Hi,
Hi,
Andrew.
hi, Dalman.
How are you?
I'm good. How are you, Daman?
I'm fine.
Good. Glad things are going well. All right.
Yeah. Sure.
Yes, Prince?
Yeah. Thanks so much today for the demonstration, at least.
Yeah, you're
Actually,
welcome.
when it comes to this completely the square, I was little bit doubting into it, but at least I got some clarity today. Thank you so much. Thank you.
Okay, you're welcome. Okay. All right, so I think I'm going to stop the recording now.